Good morning everyone. Today we will study definitions and examples in topology. First of all, we will define power set because we need it in the definition of topology. Suppose X is a non-empty set. The power set Px is the family of all subsets of X. Clearly, phi, which is empty set, always belong to power set of X. Also, the complete set X always belongs to power set of X. So, now we define topology. Topology is nothing but a subfamily of the power set Px having the following properties. We denote the subfamily by T. So, subfamily T of the power set Px is called a topology on X if empty set belongs to T and X belongs to T. If A and B are any two sets of T, then A intersection B also belongs to T. If A alpha belongs to T, where alpha belongs to some indexing set delta, then union of A alpha also belongs to T. Means arbitrary union of sets in T is also in T. If all the three properties are satisfied, then T is called the topology on X and Xt is called the topological space. The elements of X are referred to as points, whereas elements of T are referred to as T open set or simply open sets. We call elements of topology to be open set. The set X may have different topologies. Suppose T1 and T2 are any two topologies on the same set X. If T1 is subset of T2, then T1 is called the smaller topology than T2 or weaker topology than T2 or coarser topology than T2. And T2 is called the longer topology than T1 or finer topology than T1 or stronger topology than T1 or larger topology than T1. And now strictly finer topology. T1 is said to be strictly finer topology than T2 if T1 is finer than T2 and T1 is not equal to T2. That is if T2 is a subset of T1 and T1 is not equal to T2. Here T1 and T2 are the topologies on the same set X. The topologies T1 and T2 are said to be comparable if T1 is a subset of T2 or T2 is a subset of T1. T1 and T2 are not comparable if neither T1 is a subset of T2 nor T2 is a subset of T1. Means T1 and T2 are comparable if T1 is a subset of T2 or T2 is a subset of T1, and not comparable if T1 is not a subset of T2 and T2 is not a subset of T1. Here T1 and T2 are topologies on the same set X. Whatever the set X may be, the family consisting of empty set phi and whole space set X is always a topology on X, and we call this family to be a trivial topology because we notice that this satisfies all the three properties of a topology. First property is phi and X belongs to T. So here phi belongs to T and X belongs to T if we denote it by T. The second property is if A and B belongs to T, then A intersection B also belongs to T. Here it has only two elements, phi and X, and intersection of phi and X is phi, which belongs to this set. Third property is union of sets in a topology belongs to T. So phi union X is X, which belongs to T. So all the three properties are satisfied. So it is a trivial topology on X. This is a topology. We can denote it by T. So because it satisfies all the three properties, phi belongs to T, X belongs to T, If phi belongs to T and X belongs to T, then phi intersection X also belongs to T. If phi belongs to T and X belongs to T, then union of phi and X also belongs to T. If we consider an example, let X equal to AB, and we consider a power set X equal to phi X A and B, because power set consists of all the subsets of X. So it consists of two elements. So power set of X consists of four elements: phi empty set, X complete set. X instead of X we can write AB as well, A and B. If we consider T equal to phi and X, we have seen that this is a topology on X. The same example, this is a trivial topology. If T equal to Px means power set of X, in this case also it is a topology on X. Clearly phi and X belongs to X. If we consider intersection of phi and X is phi, it also belongs to Px. Intersection of X and A is A. It also belongs to Px. Intersection of A and B is phi. It also belongs to Px. Intersection of B and phi, it also belongs to, it is phi, also belongs to Px. Intersection of A and phi is phi, it also belongs to Px. So intersection of any two subsets of this set also belongs to Px. So second condition is satisfied. Union of phi X is X, it is in Px. Union of X and A is X, it is in Px. Union of X AB is AB, which is X, also belongs to X. Union of all sets is also X, so it also belongs to this. So all the three properties are satisfied. So power set of X is always a topology on X. If we consider this set, then it is again a topology on X, because phi and X belongs to T. First property is satisfied. Intersection of phi and X, phi, it is in T. Intersection of phi and A is phi, it is in T. Intersection of X and A is A, it is in T. Intersection of A and phi is phi, it is in T. And union of phi and X is X. Union of X and A is X. Union of A and phi is A. Union of phi X and A is X. So all the unions also belongs to T. So it is a topology in X. Similarly, we notice that this is also a topology on X, because all the three properties of topology are satisfied. But if we consider T equal to phi A B, then it is not a topology on X, because AB does not belong to this set. So first property is not satisfied. This is again not a topology on X, because phi does not belong to this set. So first property is not satisfied. This is also not a topology on X, because it does not contain X. So first condition is not satisfied. So if we consider T equal to phi X, T equal to Px, T equal to phi XA, T equal to phi XB, then these are the topologies on X. However, if we consider T equal to phi AB or XAB or phi A, these are not the topologies on X. Now what are the open sets and closed sets? We have seen that in the last slide that elements of a topology are called the open sets. So any set A of T is called a T open subset of X, or simply open set, and its complement X minus A is a closed subset of X. So it may happen that any set is a closed as well as open set with respect to a given topology. Now neighborhood. Let Xt be a topological space and A is a subset of X. Then A is called a neighborhood of a point X belonging to X if we can find any open set belonging to T with X belonging to G such that G is a subset of A. So to find the neighborhood of a point, we need to find any open set belonging to T with a condition that X belongs to G, which is a subset of A. Now deleted neighborhood. If we delete the point X from A, then we call it a deleted neighborhood of X. So if A is a neighborhood of a point X belonging to X, then A minus X is called a deleted neighborhood of X. Now closure. Let xt be a topological space and A is a subset of X. The closure of A is called the intersection of all closed sets which contain A and is denoted by the symbol A bar. So we write it as A bar means closure of A. It is the intersection of all the closed sets contained in X which contains A. So closure of A is the intersection of all closed sets which contains A, and we denote it, and F is closed here, and we denote it by A bar, or sometimes we write CLA to denote closure of A. So A bar is closed because arbitrary intersection of closed set is closed. Here F is closed and it is the intersection of F, so A bar is closed. Also, A is always contained in A bar. Now closed superset. If we define A bar equal to intersection of Fi as closed superset of A. Now interior point. Suppose Xt is a topological space and A is a subset of X. A point X belonging to A is called an interior point of A if and only if we can find an open set belonging to T with a condition X belonging to G such that G is a subset of A. So the interior of A is defined as the set of all the interior point of A. We also called interior point to be The interior of A is defined as the set of all interior point of A and is denoted by interior of A. So we can write interior of A equal to union of open sets G which is a subset of A. Clearly, interior of A is open set because arbitrary union of open set is open, and interior of A is always a subset of A, and interior of A is the largest open subset of A. Now limit point. What is limit point? Suppose Xt is a topological space and A is a subset of X. A point X belonging to X is called the limit point of A if every open set of G containing X contains a point of A other than X. Here it is small x. It is small x. Let Xt be a topological space and A is a subset of X. A point X belonging to X is called a limit point of A if every open set G containing X contains a point of A other than small x. It is a small x here. So we also call limit point to be a accumulation point. X belonging to X is called a limit point of A if for every open set G with X belonging to G, G minus X intersection A is not empty, is not equal to phi. So for the X to be a limit point, we should have an open set in T with a condition that X belongs to this open set and intersection of G minus X with A should not be is empty. And set of all limit point of A is called the derived set of A, and we denote it by dA. Limit point is also called accumulation point. If we consider example x equal to a, b, c, and we are given a topology t equal to phi, x, b and ac. Now, how to find interior of AC, closure of the set AC and set of all cluster points of the set AC. So, we know that by the definition of interior of a set A, which we denote by interior of A, that it is the largest open set contained in A. So, here for the set AC, because it belongs to T, so AC is open set in T, and there is no larger open set contained in AC in this topology. Because phi does not belong to this set, x does not belong to this set and b does not belong to this set. So, there is no larger open set in AC in this topology. Therefore, interior of AC is same as set AC. Now, closure of this set. The closure of set A is the smallest set containing A. We also denote closure of A as CL within bracket A, or we sometimes write A bar to denote the closure of set A. The set A equal to AC is closed since its complement is in T, because x minus AC is nothing but B. Because x is ABC, so x minus AC is B, but B belongs to T. So, it means B is open. It means x minus AC is open. So, in this case, we have seen that AC is closed also as AC is open. So, this set AC is open as well as closed. And there is no smaller closed set containing AC in this topology. See, it consists of phi, x, b and AC. So, there is no smaller closed set containing AC in this topology. Therefore, closure of AC is nothing but the set AC. Now, cluster point of AC. Cluster point is also called limit point. It is also called accumulation point. A point X is a cluster point of a set A if every open set containing X intersect A at some point other than X. So, for the set A equal to AC, B is a cluster point. Since every open set containing B intersects AC at B, because B is, for example, B is in the given topology. See, B is in the given topology. A and C are not the cluster point because the open set AC itself does not intersect AC at any other point other than A and C. Therefore, the set of cluster point of AC is singleton set B. Thank you.